Howdy, Bike 410 students. All right, so on the last video, we talked about the shape of the uh, rate of product formation as a function of substrate concentration. And we talked about how the Michaelis-Menten plot is nonlinear, but it has two parts to it. It has that pseudo first order part at low substrate concentrations, pseudo first order, and when you are at below the Km, so below when the concentration is lower than Km, and then when the concentration is high, it becomes zeroth order or zero order in substrate concentration. In other words, it becomes flat. And when you have that sort of linear phase and then that flat phase, we call that shape the rectangular hyperbolic dependence of the velocity of the reaction on the substrate concentration. Okay, that rectangular hyperbolic shape is what we saw in blue on the Michaelis-Menten plot. All right, so the Michaelis-Menten theory came out of work done in Leonore Michaelis and Maud Menten's lab, and they had some assumptions that went into this theory. In other words, your enzyme will not display this Michaelis-Menten kinetics, that rectangular hyperbolic dependence of your velocity on substrate concentration, unless these assumptions hold true. Well-behaved enzymes will hold to these assumptions. The first assumption is that you form an enzyme substrate complex. And that seems like a good assumption. If an enzyme is going to catalyze the conversion of substrates to products, it's going to interact with the substrates. So that one is usually not a problem. It also assumes that the enzyme substrate concentration during the reaction is unchanging. That's the steady state assumption. That doesn't mean that you're looking at the same enzyme bound to the same substrate. That just means as the enzyme substrate concentration, enzyme substrate complex disappears, either by K minus 1 going back to E plus S or K2, right, going forward to E plus P, that disappearance of the enzyme substrate complex is balanced by the formation of new ES. Okay, so let me say that again. The steady state assumption means disappearance of ES, either going backwards or forwards, is balanced by the formation of new ES. Okay, so you're looking at something that's in flux. These are new enzyme substrate complexes being formed all the time, but that total amount, that concentration of ES is not changing. And if you still don't understand the steady state assumption, go back to watch Sal Khan again on that second Khan Academy video. It's a very important point. And then the third assumption of an enzyme that behaves using Michaelis-Menten kinetics is that at very high substrate concentrations, so in other words, at substrate concentrations that are greater than Km, maybe much greater than Km, the breakdown of the ES complex to form products, so this step right here, is the rate limiting step. In other words, if you have lots more substrate than you have enzyme, then what's limiting is not formation of the enzyme substrate complex. There's such an excess of substrate that as soon as you have a free enzyme, there's a new substrate waiting in line to get onto that active site, right? So that's not going to be rate limiting. That's not going to determine the slow step anymore. At high substrate concentration, the slow step is actually the chemistry. The chemistry is defined by the rate constant K2. This step is the chemistry step, and it's also called the catalytic rate constant, Kcat. Okay, so K2 is equal to Kcat. Okay, so when you have a well-behaved enzyme, it will form an ES complex, check. The formation and disappearance of ES will balance so that you have a constant concentration of the ES complex. That's the steady state assumption. And the rate limiting step at high substrate concentration is going to be the chemistry step, K2, which we can then call Kcat. Okay. All right, so that's what's shown on this graph here. We're looking now at a bunch of different things. We're looking at disappearance of substrate as a function of time, shown in the purple line here. We're looking at the, formation of product as a function of time in the green line here. And we're looking at the ES complex, which you'll notice, let me highlight it. You'll notice that the ES complex is formed at early times, but then once you maximize the ES complex, so at higher, at later times, you enter this dark tan rectangle, right? This dark tan rectangle. And once you're in this dark tan rectangle, the change in the enzyme-bound substrate concentration, this part right here, is not changing as a function of time. And that's what this means, right? The change of ES concentration as a function of change in time is equal to 0, all right? That's the steady state assumption. And the reason is shown in the blue line. So if I can, so if I can change color of my highlighter, which, no, I can't. Okay, yes, I can. All right, so this blue line is showing you that all of the enzymes are fully occupied. So as you form the ES complex, all of your E total is in ES. Okay, so as you're at later time points, once the enzyme and the substrate have found each other, now the enzyme total is very low because the enzyme is all occupied by substrate. Okay, so that's the steady state assumption, that there's this part right here, that there's no change in the total concentration of ES complex as a function of time. All right, so that's the point of this slide. Now, the equations that you need to commit to memory are the Michaelis-Menten equation, which you saw derived on the Khan Academy video number 2. The fact that Vmax is equal to K2 or Kcat times the enzyme concentration. So enzyme concentration is kept constant, but if you repeat your experiments at a higher enzyme concentration, then obviously that's going to shift everything faster, because the more enzyme you have, the more ES you can make and the more product you can make per unit time, okay? And so for that reason, there is a linear dependence on your maximal velocity is directly proportional to your total enzyme concentration. And then it's multiplied by the chemistry, Kcat, constant, K2. So remember, we only see Vmax at high substrate concentration. So substrate concentration's much greater than Km. All right, and then the third equation is Km, the Michaelis constant, which is equal to a ratio of the rate constants. In the numerator, we have the rate constants that are associated with the disappearance of ES. Remember, we can lose ES by going back to E plus S, which is described by K minus 1, or by going forward to E plus P, which is described by the rate constant K2. So this is the disappearance of ES in the numerator, all right? In the denominator, we have the formation of ES. So Km, the Michaelis constant, is not only equal to the substrate concentration at 1/2 Vmax, it's also equal to the ratio of the rate constants, with the disappearance of ES in the numerator and the formation of ES, which is described by the rate constant K1, in the denominator. So you'll need to commit all three of these equations to memory and be able to use these on quiz 10 and on the final exam, the new part of the final exam.